5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Hi, welcome back, space enthusiasts. My guest this week is Dan Katz. He's the CEO and co-founder of a company called Orbital Sidekick from San Francisco. And Orbital Sidekick is putting up a hyperspectral Earth observation constellation. Now, if you don't know what hyperspectral is, don't worry, we'll go through it. We explain the technology. It's really cool tech and what the use cases are. So this is one worth listening to. Enjoy.
My name is Raphael, and I'm an investor and advisor to space companies. Just as a reminder, this podcast is for informational purposes only, and nothing should be taken as investment advice. This podcast is sponsored by NanoAvionics, a satellite manufacturer and mission integrator. Their technologies enable many space companies worldwide to offer services that improve life right here on Earth, such as providing global connectivity, conducting Earth observation, or contributing to scientific discoveries. Check them out, and also check out my episode with the CEO and co-founder. Sadly, I am not a rocket scientist, but I'm an alumnus of the International Space University. ISU offers a number of educational programs about space worldwide. Check them out at isunet.edu.
And just some final things before we start the episode about ourselves. If you enjoy the podcast, please leave us a 5-star rating on your favorite podcast platforms such as Apple or Spotify. If you want us help expand our work, you can do so and support us at www.patreon.com/Space Business Podcast, and we'll also put that link in the episode notes. And lastly, you can follow us on Twitter at podcast_space. Hey, welcome back, space enthusiasts. Time for another episode of the Space Business Podcast. Very excited today to talk about another really cool Earth observation business. And my guest for that is Dan Katz. He's the CEO and co-founder of Orbital Sidekick. Welcome, Dan.
Thank you so much for having me. Pleasure to be here.
No, it's great. And Dan, why don't we start off as usual? And could you please give us the elevator pitch on Orbital Sidekick?
Absolutely. Happy to. So at Orbital Sidekick, we are building the most robust remote sensing and analytics capability in existence with a core focus on sustainability. And that means that really from a logistical standpoint, we are launching a constellation of hyperspectral satellites. Happy to go into what hyperspectral means a little bit later. Launching a constellation of hyperspectral satellites to monitor on our go-to-market strategy is energy infrastructure. So specifically oil and gas pipelines for methane leaks, oil spills, regulatory compliance. So we leveraging this constellation of hyperspectral satellites. It provides global persistent monitoring service for our customers. And we have So we're pretty vertically integrated. We have our satellites. We have we collect the data. We analyze the data ourselves in house to extract actionable intelligence, and then we deliver that intelligence, those insights directly to our end users on the ground. And so, we're based in San Francisco. We're a relatively modest sized team. We run pretty lean, about 30 of us here. We've got we've had 2 missions launched over the last few years and 2 space missions, and we have 6 more satellites slated for launch in 2023. Just excited about the progress so far.
Okay, very cool. So let me just ask you to define like a few of the terms you use there.
Sure, absolutely.
So, I mean, for better or worse, since this is meant to be a podcast, so that also non-technical people can follow along. Do you mind sort of quickly summarizing what hyperspectral actually means and how it's different from some of the other Earth observation sensors that people may be more familiar with?
Yes, absolutely. And so, right, there's a lot of different modalities out there in Earth observation these days, which is really exciting. I'm happy to dive into some of the other ones as well and where hyperspectral fits in. But the way I like to explain hyperspectral is kind of, let's start with the camera that's on your cell phone, right? It's when people take a picture. Generally, you're looking at visual data. You're looking at 3 wide color bands, red, green, and blue, that are combined together to get the image that you see on your phone or on your camera. And that gives you, object spatial information. What's the shape of that object? And what's the color of that object in a small region of visible light. With hyperspectral, what we're doing, instead of just those three data points of red, green, and blue, we're looking at hundreds of color bands in the visible and infrared light region. So instead of 3 data points, we have 500 data points. And what that allows us to do is basically chemically fingerprint each object in our data set. So everything reflects and absorbs light in a unique manner. And we see it in the visual spectrum, and that's how we can identify something as green or red or blue, or some variation of that. But there's other absorption and reflectance features that present itself in the infrared light region. And hyperspectral allows us to look at visual and infrared with a very high spectral resolution. And so we can identify those absorption and reflectance features. And that allows us to, as I said before, basically chemically fingerprint that object. So methane is kind of the hot button topic today. So methane is not something that you are going to see if the methane gas or CO2 or other types of gaseous emissions or plumes. It's not something you're going to see with the naked eye or with the camera on your cell phone. But with hyperspectral, because methane has very unique absorption features throughout the electromagnetic spectrum in both visual and in the infrared region, our hyperspectral cameras can identify those features and therefore identify a methane leak. And there are hyperspectral, and Earth observation in general is pretty application agnostic. But what we found is that for our go-to-market strategy, really focusing on the energy sector to be able to identify things like methane leaks, but also looking at oil spills, so identifying the spectral signature of the oil spill, or erosion or land movement or topographical changes, changes in vegetation along a pipeline right-of-way due to an underground leak of methane or oil. So that so if like a healthy plant is going to have a different spectral signature, a different way that our camera's going to see it differently than it is a dying or unhealthy plant or something that's been starved of, say, oxygen due to an underground leak. So there's all of these different, really, the clever marketing thing is, right, you can see the unseen, or making the invisible visible, however you want to put it in that sense. But the point is that you're really just amplifying to orders of magnitude your ability to see beyond just what your eyeballs would see or what a normal camera would see. So that's the really exciting thing about hyperspectral. And what the other thing as well is this technology, we did not develop hyperspectral technology. Like Orbital Sidekick did not. This isn't like a brand new thing that's unique to us necessarily, but it's been around for a while. But it's been generally relegated to either government programs, like large, like defense and intelligence programs, or it's been on the commercial side. There's been some use for it for precision agriculture. I mentioned before about looking at vegetative stress or disease or other things that be used for. But at a very small scale, maybe, either handheld sensors, maybe in an aircraft. But because part of it, as I said before, you have, your normal Earth visible range cameras that are on a lot of Earth observation satellites today, like with Digital Globe or Planet or Black Sky and others, which are very useful for their case. But again, they have three data points per pixel. So you have for lack of a better word, let's call it 3 bits of information, where we have 500 bits of information per pixel. So that's a huge amount of data to manage and handle, right? You have over 100 times more data per image.
Sounds like a data scientist's dream.
Right, exactly. And so whereas a couple, maybe even 10, 20 years ago, doing large scale hyperspectral projects was really challenging because it had to be done pretty manually. but now because you have cloud compute capability, you have onboard processing, edge compute capability, like we process data actively on our satellites to try to reduce the data burden. These are enabling technologies that we can tie into and leverage to make this possible, where again, like 10, 15 years ago, this company could not exist with the lack of infrastructure that was in place before. So,
because I guess in terms of the variables, you have 500 bands, and then I guess you would have the coordinates, right? And the timestamp, right? So it's really it's really quite a big data set.
Yeah, all of the metadata that goes along with it, right, and everything like that too. So it's a huge amount of data, and this is not unique to hyperspectral, right? Of course, there's there are other, and there's also so you have hyperspectral, and then some of your listeners may be familiar with like Landsat, which is a NASA NOAA satellite that everyone on the planet has seen Landsat data because they use it for Google Maps, and it's at a lower resolution, and what they use is what they call multispectral.
Yes.
And so
I was going to ask you. So what's the difference? But
exactly.
It just means fewer bands, right?
At the end of the day, it means fewer bands. And to be honest, there's some amount of subjectivity, I think, of what's the threshold to go from like a multispectral to hyperspectral. I think generally once you are, in the, 10, once you get above 10, 20 bands, maybe that's when people start thinking, okay, that's more like the hyperspectral-ish range. But it's almost like a marketing thing. I would say that so Landsat has, I think, like 16 bands also they have various Landsat satellites that have better tech than others. And so, like 12, 16 bands, kind of like your multispectral range. Yeah. So with like I said, hyperspectral for us, I think we think of it as when you have like 100 or hundreds of bands. I think that's more kind of what we're thinking of, because that's when you are really looking at that really fine spectral resolution, and you can see those, you can really identify those unique absorption and reflectance features in a spectral profile. And with multispectral, you're not really getting that. You just kind of have, it's still very broad buckets of spectral information. So you're not going to be able to do that same chemical thing.
Yeah, and hyperspectral, it sounds cooler than multispectral, right? It sounds like it's going to add like 50% on your pre-money valuation just by using.
And now, of course, right? And then of course, now there's people saying, oh, there's ultraspectral, and that's thousands of spectral bands, or there's you can, the marketing behind it, you can do whatever you want on the name, the nomenclature. There's all sorts of things you can do. You can, maybe you don't need the high, like you can. So one of the nice things about actively having our own satellites that we have is that we can control our sensors and kind of what bands we focus in on to get higher resolution, or both on the spatial side and the spectral side. And so we can have, there's a lot of, so certain customers might want higher spectral resolution, so more bands in the visible region, or they might want more spectral bands in the infrared region. So we can actively select and kind of have that almost bespoke capability for certain customers, which is nice. And so as you're looking at, I think that really the key thing here is just, whether it's multispectral, hyperspectral, or ultraspectral, whatever it is.
Ultraspectral.
The key thing here, though, is that you always, like, hyperspectral is not necessarily the best answer to every problem. And maybe the key, though, is to identify what is your go-to-market strategy and what problem are you solving? And so does your technology align with that? And not just to get caught up in, I just need to get the most spectral information.
Which is, of course, typically what happened with engineers is sort of like, we can have more bands, let's have more bands. But so I was going to ask you, I mean, in terms of the bands, so actually I learned something new. I didn't know that I was going to ask you whether there was something coming up beyond hyper, and I guess there is ultraspectral. But is there sort of an upper bound that, and it could be, I guess, is there an upper bound in terms of, I guess, the physics, the technology, but then kind of alluding to, or so kind of going to what you're alluding to, is there an upper bound also beyond which it just kind of becomes commercially stupid, for lack of a better word, where it's just you don't need higher spectral resolution anymore?
Yeah, I mean, I think so there's always a trade-off, and when you add more spectral, when you get finer and finer spectral resolution, you are limiting the number, and I'll try not to get super technical on this, but just I'll start pretty technical, and then we can zoom out from there, right? Okay. So at the end of the day, you want, when you have a telescope and then you have a camera behind it, you're bringing in light and photons of light, right? And if you let's say I just had one spectral band, like a panchromatic camera, which the digital globes, some of them have that, and they get really high spatial resolution. But they have one spectral bucket, then all of that light and all the photons of light can go into that one spectral bucket, which is good because you want good signal, right? Sure. Signal to noise ratio is really important. And if your noise outweighs your signal, then it's going to be, I guess in just lack of a better term, you won't be able to differentiate what's in your image, and it'll just be noise, and it's useless. As you add more spectral channels, you're effectively dividing the light that comes in, the amount of photons, into more and more buckets. So each bucket gets fewer and fewer photons, right? And so that hurts your signal. So at a certain point, it's a diminishing rate of return, because you're just going to have such, like, okay, you have thousands of these spectral channels, but you're dividing the photons into all of these. So the signal to noise ratio is just very poor spread out across. So it doesn't even, so you lose. And then what that means is like, oh, well, I have to increase the size of my telescope then, and get bigger and bigger and bigger and bigger. So now, like, we have a 45 centimeter aperture telescope in front of our camera, which is big, right? That's almost it's a large light bucket to let in. So because we want as good signal to noise ratio as possible for hundreds of bands. But if we were to go to thousands of spectral channels, then now we're talking about like a 1 meter diameter telescope or bigger. And that's massive, right? I mean, you're starting to look at, like, now you're starting to look at like the digital globe worldview satellites, which are, $500 million satellites, massive, or now you're looking at NASA type programs for $1 billion programs that have these 2 meter telescopes, right? It's a massive undertaking. So there's a physics limitation, and there's always a trade-off. And then, actually we started out, and this is, so physics rears its ugly head when it comes in hyperspectral, unfortunately. And so there's always a trade-off. And then, so the key is to not, like, I'm an engineer by training and physicist by like academic background. So, I mean, I'm always for like the next, I always want better and better and better tech. But what's been very grounding for us is having this kind of vertical structure where having the satellites and the data acquisition and the analytics and the product, the end user product development, all in under one roof, we can be very, it's like, okay, we don't need, like, we know exactly what we need to deliver the product to our end users. So And that helps us to stay focused on what problems we need to solve and which technology we need to develop. But so.
Makes sense. Okay, so just coming back to, because you mentioned the photons, and I realized I should have asked you before for the benefit of probably most of our non-technical listeners, where does that leave multispectral and hyperspectral technology and sensors with regard to operating at nighttime and cloud cover?
Yeah, no, it's a great question. So, looking at visible to near infrared light region, so which is like the 400 nanometer to 1000 nanometer wavelengths. which is a lot of companies are kind of in that range. You're really limited to you're really limited to the daytime no cloud conditions. We go farther into the infrared. We go all the way up to 2,500 nanometers, and that allows us to we can't necessarily see through clouds to a very good degree, but there are certain things we can that we can see, and especially when it comes to you start looking at emissivity from like very hot events like fires or explosions or plumes, things that are more on the defense and intelligence side, honestly. And so that's that's the other side of our business, by the way. So we have energy customers on the commercial side, the oil and gas customers and others there. And then we have defense and intelligence as the other half of our business. So, we have, that is, so there, right. I guess in short, we are ideally we would have, clear skies during the day. Like that's our bread and butter. And that's how we kind of baseline our capacity and how we expect to perform. But there is some limited operation that we can do in cloudy and nighttime conditions. But those are generally reserved for non-commercial operation. And then, but I do want to we're not like a SAR. So you're right, the synthetic aperture radar folks, they are like we don't have the performance at through clouds.
Yeah, sure. But that's I guess the other thing we should point out for the non-technical listeners, right? Because SAR is an active sensor, right? This is passive, right? What you guys are doing.
Absolutely, right. And so right, there's always pros and cons of any technologies, and so right, and so SAR has that that passive sensor capability that allows them to see at night and through clouds, and it's a really powerful tool. But the downside of SAR, of course, then is that you're really only looking at kind of one data point per pixel. What's the elevation, right? So but what's a really powerful thing is combining SAR and hyperspectral, and that's something that I'm happy to chat about too. Is how I think I said this earlier, that hyperspectral is not necessarily the end all be all for Earth observation, and no single modality is, right? There's no magic bullet that's going to solve every single problem. There's always limitations to every single modality and phenomenology. So I think data fusion is going to be increasingly important as we have more access to different commercial constellations. So a fusion of SAR, hyperspectral, and high-res optical. That's going to be a very powerful product. It's something that we're already looking at doing a bit on the commercial side. And then, of course, a lot of our government customers are on the intelligence community side, are very interested in data fusion and how we're putting all these modalities together.
So speaking of data fusion, I mean, okay, even before you fuse it with other sensors, I mean, just as we talked before, like 500 bands and all of the metadata, I mean, this is just a ton of data, right? And so never mind, like you pointed out, of course, we now have the capability here on Earth to process this in a very effective way and do machine learning. But we do have these, at least for the moment, we even on this podcast, we talk regularly about, the bottleneck of bringing data back to Earth, right? Are you guys doing any onboard processing with this, or are you actually really sending the whole batch back to Earth?
Right. So we're absolutely doing onboard processing, and we are bringing certain data sets back down to Earth as a whole. So it is customer dependent. So again, on the two halves of our business, and they complement each other for this reason. So for the commercial side, so if any commercial customer, they're not well versed in hyperspectral. They don't have a room of hyperspectral data scientists and PhDs like we do, who can analyze the raw hyperspectral data and apply the algorithm and get the intelligence. They don't want to do that. That's it's not to their best interest. So we just give them the intelligence, and so the good news for that is that so that we can do a lot of that processing on board. We know which signatures we're looking for. We're looking for the methane signatures and the oil signatures, the construction activity, and a lot of other features and products that we have for our customers. We can do a lot of that on board and just identify where that anomalous condition occurs and basically just send down a GPS coordinate, right? Just a few kilobytes worth of data. That's not actually really an image. It's the intelligence, right? Where is that incident occurring? And so that obviously helps immensely with our data burden for our commercial customers. Now, if we do find a very high value, if we do find a methane leak or something like that, we will generally bring that data down eventually as well. And we do have very high throughput radios on our spacecraft, so we can get gigabit per second downlink capability, which helps alleviate those issues. But we're not planning on bringing down all of the data we're capturing. On the government side, they are more interested in getting the whole data set, but they're starting to lean more into the onboard intelligence as well, which is really fascinating. And so these are things that we're actively kind of working to see how this is going to be fleshed out on the delivering derived analytics products on the government too. But yeah, the data bottleneck will continue to be an issue, especially as we continue to add capability to our constellation in the future, get bigger swath width so we can get more coverage, more satellites, just more data. And our data scientists always want more training sets, so they would love to have us bring down as much data as possible. So like I said, how do we solve that? Onboard processing, high throughput Ka band radios for gigabit per second rate downlink, more ground stations to allow us to download more frequently. And then the last piece, while we don't have them integrated yet on these first 6 satellites we're launching this year, we are already in process of getting development work for the next 8 satellites after this that we will have optical inter-satellite relay.
That was my next question. Yeah, that makes total sense.
Yeah, so the OISL, I think the explosion of OISL demand with the SDA transport layer, so the pull on the government side has been really great to help spur innovation there and demand. And then, so I think we're still trying to figure out the commercial cases there. For our commercial customers, I'm not sure that the OISLs will be a major differentiator for us, but certainly on the government, the low latency data capability or data downlink capability is going to be critical. So I think that's something that we're very excited about integrating for our next generation.
Yeah. And then how does your business model then actually work? It sounds like for your, at least for your commercial customers, maybe for the government as well, it's a lot basically the customers actually specifically tasking the satellite, right? Probably to look at a certain facility or something. So I was wondering how much of that your business comes from that versus maybe you're just collecting data, building a library, which you can then monetize. Is it one or the other, or is it both?
So the main, on the commercial side, what we do, and so for the oil and gas pipeline operators, so let's say, so we have, there's some stuff is public, others is not public yet. Hopefully will be soon. So we have we have a contract with Energy Transfer, which is one of the largest pipeline operators in the world. They have 120,000 miles of pipeline in North America. We're not monitoring all of those pipelines yet. Our goal is to get to that point. But so if you have hundreds of thousands of miles of pipeline, the idea would be that we would sign effectively a monitoring services contract that on a routine basis, we will be capturing data over your 100,000 miles of pipeline on, let's say once a week, and it will be at at this dollar amount per mile per revisit. Okay. And so that's how you build that model. So it's really based on monitoring frequency, and there's not much change, right? Like pipelines are stationary. They're not really like moving the targets around, right? So it's like, okay, we know where your pipelines are. We're going to be monitoring them frequently, and then we'll just charge you based on how frequently you would like them monitored. And then there's analytics package on top of that, right? So I let you know if there's a methane leak or construction activity, if there's topographical or erosion changes or vegetative changes along the right of way that would indicate an issue. So, and that all is under a regulatory compliance bucket. There's pipeline operators have to apply with certain government regulations to ensure the safe operation of their pipelines. So that's kind of how that monitoring service package is built, and that's that initial go-to-market. And from the, and then there's, if they have certain fixed facilities or offshore facilities, we can add those in. But yeah, it is mainly task-based in that sense. We're not strip mapping the entire globe like Planet Labs is. We just don't have it. Yeah, part of it is that capacity issue and downlinking issue of trying to all that hyperspectral data down, at least initially. Eventually, though, so with the first 6 satellites next year, it's really specific to the paying customers, and then on the government side, they have tasks that they're going to want us to do. I'm sure monitoring Ukraine and all the Syria, North Korea, like those kind of areas, right? On the other side of the globe. Then you have, but eventually, once we get another 8 satellites up, so once we have 14 total, then we will be able to map more completely the entire globe and look at more developing a hyperspectral atlas of the globe, and then being able to sell access to that type of archival imagery and data. So that's our kind of our growth strategy at the moment. But yeah, it'll take a little while because of that massive data burden to kind of build up that capacity.
Yeah. So your total target size was 14 satellites. And so what kind of coverage, you said that's global coverage, and what kind of revisit rate would that get you to?
So, but 14 is kind of like on the next one. Honestly, we're actually putting in place a production line type capability where we plan to put up many more than 14, but that's kind of just the next block getting there. So once we get to 14, though, that means that we'll be able to map every inch of the globe with hyperspectral imagery every week. But then because we have pointing capability, we'll be able to image most of our customers every day, and certain customers multiple times a day. So it really kind of depends on where exactly or what kind of the use case is. But the kind of the general sizing is that getting to that kind of a weekly hyperspectral atlas capability, and then from there you target specific customer needs on a multiple times a day basis.
And I guess while we're talking about resolution, and so we already talked about spectral resolution, now temporal resolution. I guess the remaining question, one of the remaining questions, is then spatial resolution.
Right.
And I guess that's a little bit different for you guys, right? Because I guess maybe it's not that meaningful to think of like, oh, it's like X inches. I guess because you at least for now, you're sort of looking at stuff like methane leaks. Is it sort of are you looking at sort of like parts per million resolution? Or how are you kind of looking at this capability?
Yeah, it's always, spatial resolution is, it is an important piece of the puzzle. It's not something that you can ignore, and then it goes into your the precision and the thresholds for how you could detect certain spectral features. So if your pixel size is very big, like let's say you have a 30 meter GSD, so 30 meter pixel size, which a lot of hyperspectral satellite tech has kind of lived in that 30 meter GSD historically. It's, that's 30 meter by 30 meter, that's 900 square meters of, of land or ocean, wherever you're looking at. So you have, you generally, best practices, you need at least 20% fill fraction of a pixel in order of a certain substance in order to identify that substance is in that pixel. Otherwise you get too much, it goes back to signal to noise ratio, spectral mixing, all that stuff. So if you have a plume of methane and you're trying to fill 20% of a 900 square meter pixel, you need a pretty big plume. So So that's kind of one way to look at it. There's obviously a lot more other ways that you can look at it too, but that's kind of, I think, a good way to start. So for us, what we did is we'll say, okay, using that kind of 20% fill fraction concept as a baseline, where it's like a happy place for us to live. That's also is going to allow us to get signal to noise and not blow up the cost of the spacecraft. We don't have to build a 1 meter telescope and things like that. So we came in at about 8 meter GSD, so 8 by 8, so that's 64 square meters. So 20%, right, of 64, you're looking 12, 13 meters, and that ends up being closer to the 100. Well, we think of it not as a ppm or ppb for methane. We look at rates. So what our customers want is somewhere around the 100 kilograms per hour rate for a release. So that, I think that's kind of the happy place for space-based methane monitoring, about 100 kilograms per hour. Trying to get less than that is a really, really big challenge. There's a lot of factors that can go into affecting those calculations. And then also for 8 meters, that allows us to do like vehicle detection, construction activity, which is a really big threat to, and security threats as well, which are really the like other piece to not just pipeline monitoring, but for a whole host of other kind of infrastructure monitoring. So that's kind of where we're living in, that kind of 8 meter GSD for hyperspectral. But yeah, it's not quite the same as, you're getting 30 centimeter GSD for the WorldView digital globe satellites.
Sure.
And so, but it's not a 1-to-1 comparison. We actually have a panchromatic camera that also on our system, it takes advantage of the same telescope, just a different camera on the back end. So we can get down to 1.5 meter GSD in our panchromatic camera. And in future generations, we'll have down to about 50 centimeter GSD for our panchromatic. So it's only a single spectral channel, but allows us to contextualize some of the hyperspectral data. So we're obviously not as concerned about spatial, but it still plays a role in kind of the fidelity of the spectral information you're looking at. But it's always a balance, and it's always kind of going back and forth, and everything is always a trade. It's GSD versus signal to noise ratio versus size, weight, and power for your satellite. So it's these are the complex problems that anyone in Earth observation always having these challenges. And same with it's hyperspectral, it's optical, it's SAR, it's everyone, right? So there's always the trade-offs.
Yeah, and so just a couple of follow-up questions on that to try to make it more sort of practical or tangible for people. So one, I think probably every listener has heard or knows that there was this famous pipeline leak of the Nord Stream 2 pipeline between Russia and Germany. I assume that was sort of like the mother of all leaks, right? I assume there was a massive leak, and that you would have detected that, and other people would have detected that from space, right?
Right. Yeah, and so there's some. You have the Nord Stream pipeline. There's a massive methane leak in Los Angeles here in California, called the Aliso Canyon methane leak from maybe about 6 or 7 years ago. That was another massive release that some satellites were able to detect, even with very low resolution, because it was such a massive leak. So I think those big, massive super emitters, those are obviously very important to identify, and those are things that we can identify. However, those are ones that kind of the obvious ones, right? Okay, clearly there's a leak there, and the operator is 99% of the time, those massive leaks, they're going to know it pretty quickly, right? Because it's a huge release, and there's other systems they can have in place. The problem that we're seeing a lot in the industry is the kind of those ones that are just under the super emitter kind of classification. They're big enough to have substantial effects on contributing to greenhouse emissions and product loss for our customers, but are under the threshold of what maybe some of their existing monitoring systems can identify, like pressure transducers within the pipeline, or just day-to-day field operations. So that's where that 100 kilograms per hour range, I think, is really critical, because that makes up a huge bulk of the releases that exist, and then contribute to, like, when taken together in the aggregate, can start to outweigh these massive super emitters that people are going to identify anyway, just because they're tens of thousands or hundreds of thousands of kilograms per hour or millions of kilograms per hour that are, I mean, you're going to see the nuclear bomb go off, but you're not going to see like the pipe bomb go off, right? So you have it's that kind of level, right?
And for the smaller leagues, I mean, you mentioned field operations. I mean, are there any alternatives that are really viable? I mean, do people like fly drones? But I guess drones have a limited range, right? So it becomes very complex.
So there definitely are aerial solutions that exist, and we've actually partnered with some of them. And I think it's still a bit of a system of systems type of an operation. So we view ourselves as kind of this persistent eye in the sky kind of safety blanket to monitor those 120,000 miles of pipeline for energy transfer, right? Our goal is to eventually monitor all of them, but it's spread. Those miles are spread all across the North American continent, right? So trying to monitor that with an aircraft or much less a drone is a very daunting, operationally expensive proposition. But let's say we identify an issue. We say there's a lot of problems occurring in this area of your pipeline. Then you can deploy a drone or a person in a truck to go, I look at the more micro scale, monitoring of that area. So we can help deploy certain resources much more effectively and efficiently.
Okay, understood. Just a couple of questions to finish up on sort of the tech architecture, and then I do want to talk about the customers a little bit more. So the 45 centimeter aperture, so what kind of satellite size does that translate to in the end? And I also wanted to ask you, like, why you guys decided to build your own satellite rather than hosting this.
Well, happy to address both those. So that means that 45 centimeter telescope aperture, that means that we have the mass of the satellite is almost exactly 100 kilograms, which I think falls squarely in the kind of small sat or microsat region.
Yeah.
Right. Right. So it's the size of we were in the manufacturing space yesterday. I was trying to think of a way to what's a good analogy for them, because it's bigger than a dishwasher. Maybe it's the size of like a washing machine. Maybe that's a good way to think of it. And then so we don't build the satellites in-house. We do contract out the actual build. So we work with a company called Astro Digital.
Sure.
They were about an hour away from us here in the San Francisco Bay Area. So they have a manufacturing facility, and that's where it's all put together, assembled, integrated, and tested. But I think we did look at hosted platform at some point. We had talked with Loft Orbital, who's another like a hosted platform, and a few other folks. The challenge is really, it comes the telescope we have is I think one person once described it as very fluffy, in that it doesn't weigh a lot, but it takes up a decent amount of volume, so it's hard to be on a shared platform with a lot of other payloads. And while we're not very power hungry, we are data hungry. So trying to share downlinking and things like that is a challenge. And then of course just having and then having the operational control of your own and not having to worry about other payloads or other things on there. It's just it just didn't really make fiscal sense for us. So we're really happy with our manufacturing partner. People are able to do that and do it really well. We didn't. So I think that's just kind of the model that worked out best for us.
Okay, and this is the satellites are flying in what orbital altitude?
So they're going on the SpaceX rideshare missions, the transporter missions. So those are all launching to sun synchronous orbit. So for the listeners who are more of like a polar orbit, and they're launching to nominally 525 kilometers altitude.
Okay, so you guys, this is always an interesting question for many people these days. Any constellation operators, how much are you guys thinking about sort of like, space debris and ultimately having to do collision avoidance maneuvers and how to do this? I assume you guys have onboard propulsion, that whole sort of complex of topics.
Yeah, no, that's a great question. So we are. It's always a concern, and we actually. Interestingly, we do not have onboard propulsion for these first 6 satellites. We're still weighing whether we're going to add it later because we do meet the deorbit requirements of the FCC without propulsion.
Sure. I'm more thinking sort of like in case you have to move out of the way.
No, of course. So what we've seen from I like to say I'm a recovering propulsion engineer. That was my job before starting this company. So I very, very well versed on the propulsion technology and the use cases for it, mainly for geostationary communication satellites, but also for some LEO small sats as well. But I think the collision avoidance stuff that you're seeing, the propulsion itself, I'm not sure if it's really adding a lot of value to that. It's almost more of a PR value, I guess, to say, we were notified that there's 1 in 10,000 chance we're going to get hit, so we have maneuvered out of the way. That really hasn't come up as necessarily a big driver for us to add propulsion. Propulsion for us would be come into play if we were to maintain our orbit or change altitude, like lower altitude to get higher resolution. That's kind of how we look at it. I think in general though, space debris is going to, in the future, it's going to continue to be an issue. I'm just not sure if propulsion is going to be the solution for trying to avoid it. I think, it's going to be more of a, how do we get people to ensure that they are responsible operators and deorbiting in a time that is responsible and not cluttering unnecessarily the LEO space with tens of thousands of satellites.
Okay, let's shift gears and talk a little bit about the customer side. So one thing that I'm always fascinated with and curious about when we talk about business models like this, where it's using space technology, but clearly for the benefit of and selling to a non-space customer group on Earth, like in your case, I guess let's leave the government customers to one side. That's a special case, right? But like the energy customers, right? The oil and gas customers, who probably by and large people who don't really, I assume, have much space knowledge, nor do they technically care that the data comes from space. How was it trying to sell to those people? And talk a little bit about that experience. You're kind of penetrating a non-space savvy customer.
Yeah, I think that's a great question, because I think that question should be posed to anyone operating a space business, because at the end of the day,
I do.
While space,
as a venture capitalist, I do.
Right, because at the end of the day, because space is sexy. And people like, and that can help to get your foot in the door occasionally. Like, oh, there's this kind of cool space company that wants to talk to me. And that can pique people's interest and maybe can help you get your foot in the door and differentiate from some of the other non-space solutions. But very quickly, if you can't show that this, at the end of the day, this is going to either help make your customer more money and or save them a huge amount of money and be, and help them with regulatory items and be a good, PR tool, and then add a tremendous amount of value, then the space thing that wears off very quickly. So you really have to have it's like space is just that opening salvo to maybe get your foot in the door. And then after that, it's almost not even part of the discussion. It is, what is the value you're bringing, and how am I solving a very specific problem that's going to make you money, ideally make you money, if not save you a ton of. So I think that's always been critical for us. And that's why we've been very focused initially on this go-to-market for the pipeline operators, because we know we can do that. And it's been resoundingly accepted and we're starting not only number of contracts we're getting, but even strategic investment from these pipeline operators now too. So that's the big signal, and that's needs to be the focus, and not just get like the space stuff and even the hyperspectral stuff. That also is not, they don't really care about that. It is really solving the problem. So the space and hyperspectral should be effectively a black box to the customer. It is, what are we solving? How are we solving it? That's has to be the focus. And if you fall too far in love with your technology or the fact that it's space, then you're just going to be a flash in the pan. So that's, I mean, it's a hard lesson to learn, but that's the reality.
Yeah, as a VC guy, space VC guy, I fully agree. And I really hope that listeners who are thinking about being space entrepreneurs, at least the ones who are space entrepreneurs selling to non-space customers, they really need to take that lesson to heart, because at the end of the day, the customer doesn't care. It's from space. So where then, I don't know, 10 years down the road or whatever the right time frame is, what's your vision for the company? Where would you like the company to see? Where would you like to see the company, rather?
Right. No, it's a great question. So obviously we're adding more and more capacity when we launch more and more satellites. And really what we're really interested now is what we're seeing a lot of our energy customers really interested in is this whole life cycle management and life cycle monitoring service capability, from tracking hydrocarbons or methane or oil from extraction from the ground, so oil wells and methane fracking activities, through transportation, so pipeline monitoring, consumption, so consumer and industrial consumption, and then the last critical piece, offset. So, and that comes into play with looking at carbon credits and carbon credit marketplaces. We think that Orbital Sidekick can play a role in every single part of that life cycle, and in terms of monitoring and ensuring that emissions are being accounted for and limited to the highest degree possible, but also tracking each molecule of hydrocarbon from cradle to grave. And then that will help with how companies look at their offset requirements, and then not just helping with the accounting of how many offsets an energy company may have to purchase or obtain to comply with regulation, but also being good stewards and building social trust and license to operate. But then also the carbon credit marketplace itself. How is that going to? There's the regulatory carbon credit marketplace, mainly more in Europe and other regions. That's very substantial. But the voluntary carbon credit marketplace is growing very fast. Now, one of the issues, though, is that it is highly unregulated, and people don't really know how to trust that the offsets are doing what companies say that it's doing. So because we have this very, very high accuracy, precise way of measuring not just GHG emissions, but also what we've found is that with our vegetative monitoring, we can do carbon mass measurements. So we can measure the effective carbon mass in any kind of plants or trees or areas like that. So that's really critical for these carbon credit offset programs, which are looking at saving rainforests in Africa or South America or other regions. So, being kind of that rating system, if you will, for carbon credit programs, and therefore lending validity and trust to these carbon credit marketplaces, I think will really allow those marketplaces to take root and be a very actually mature into a place where we're going from $1 billion market to $1 trillion market.
Makes sense.
That's kind of, and that's not even 10 years out. That's something that we're looking at in the next few years. But I think it's really about being the trusted, verifiable source of intelligence on a global scale for both commercial and government partners, by providing that chemical fingerprinting for every square inch of the globe. I mean, that's really the goal. And I would also love, I'm a space geek as well. I would love eventually send our spacecraft out beyond the Earth as well. Always be a dream. Sent to Mars, or the moon, to Mars, asteroids, all that. I mean, those are kind of like the very far out things, right? Because I think hyperspectral
chemical
has a huge role there.
That would be fascinating. Yeah. So that's kind of looking in the future, and I should have asked you before, but looking in the past, can you just give us sort of the brief summary how you got to do this? How did you come up with this business idea and decide to found Orbital Sidekick?
Yeah, we so my co-founder Tushar Prabhakar and I we worked at a company called Space Systems Loral, which is now part of Maxar.
Sure.
And we had been working on some of the large geostationary communication satellites, but we're also working on we actually worked a bit on the SkySat program for Skybox, which is now part of the Planet. And there was a bunch of other advanced systems programs we were working on as well. And so this is kind of the early 2010s. And just noticing that people were really focused on building space infrastructure, throwing satellites up with high-res optical instruments, but not really having a solid go-to-market strategy, kind of like a if we build it, they will come kind of a market strategy, which was okay at the time because space was sexy enough that I think venture money was flowing, but there wasn't really a solid revenue plan, and again, it was really focused on high-res optical. I've got a background in astronomy and astrophysics, and so I knew about hyperspectral imagery mainly for looking at celestial objects, chemical makeup of stars and planets. And Tushar had also previously worked for some energy companies, energy startups. So we kind of combined all of this together into a business plan where we said, well, let's use high spectral resolution data with small sats in order to solve a real problem within the energy sector, which is these pipelines are just monitored very ineffectively and efficiently, and methane emissions is a huge problem. And there's a whole host of other market opportunities that this technology can unlock. So that's kind of the origin story, if you will. It was kind of many nights and weekends of just putting that together, and then we formally kind of kicked things off. I would say bootstrapped for a little while, and starting in 2016, just really tightened things up and made sure we had everything ready, and then got kind of outside funding end of 2017, early 2018.
Yeah.
And just grown from there.
What's a quick question? What's the story behind the name Orbital Sidekick?
I think it really speaks to the way we view ourselves as partners for our end users. So when we talk with a pipeline operator, we're really saying that we're providing a monitoring solution and service to you, but it really is a partnership where we're helping you achieve your sustainability goals, your operational excellence and integrity program goals, and really helping usher you through the energy transition. And so we're your sidekick in space that's helping you achieve those.
That makes sense. I think somebody should start a company called Orbital Wingman.
There you go.
Nice. Sorry if that's too similar to your company, but anyway, so just beyond Orbital Sidekick, any sort of other interesting trends you see in EO and space in general? On EO, it could be anything. Like, I don't know. For example, are we done with all of the sensors? Is there stuff missing on the sensor side, or anything else you can think of that could be exciting in EO and in space at large?
Well, I think we're rounding out a good amount of the phenomenology. I'm sure there's others as well. I mean, I know we have SAR, but continue to do I think there's more innovation on the SAR side with LiDAR that could come into play. Yeah. I think, like I said, continue to add more spectral bands. I'm sure some people will continue to look at ultraspectral and things like that, and higher res optical, and so I think that's just, continue to push the boundaries there, lower and lower resolution, more and more spectral. What I think is going to be interesting now is the in-space servicing, assembly, and manufacturing marketplace, and how that is. I think we're still pretty far away, 5 to 10 years out, but the infrastructure is starting to be thought through and built out. And so are we going to, how are we're looking down, but, we can look left and right when we're in space and help with that kind of that in-space servicing, assembly, and manufacturing marketplace, which I think will eventually be very critical as we look at a lunar outpost and or lunar gateway, and continue to become more of an interplanetary civilization. So that's kind of what I've been looking at a bit, or what's very intriguing to me, I should say. And the government's investing in it too, which is really interesting as well.
Fair enough. And then I think, our final question, the podcast is always the same, which is about science fiction and your favorite science fiction, which could be anything, movie, TV series, books.
Yeah, I mean, my favorite science fiction series is I believe it's called Remembrance of Earth's Past is the series name, but it starts
it's the trilogy.
The three body problem and the Dark Forest and Earth's Past. I think that's probably my favorite. I've read that series at least twice. I think maybe excerpts of it even more than that. So I think it's a fascinating piece. I think it's definitely made me rethink about whether we should be sending any signals out into the universe. The Dark Forest theory definitely makes me nervous about certain things, but
that ship has sailed with the golden record and everything.
Well, yeah, I mean, I suppose, but I think it's we'll see how things play out. Hopefully, I'll try to be optimistic, but.
But amazing books. I fully endorse that. That's probably the best written science fiction I've read since the classics. I would say so. Yeah, highly recommend to everybody. Yeah. Dan, when's your when is the next launch of your satellites?
So the next launch is the next SpaceX rideshare in early next year, Transporter 7. So I think that's currently slated for like March, April timeframe. As we get closer to launch, I think that date will get defined. Transporter 7. Yeah.
Terrific. Exciting times, of course. Best of luck for that. And look, it's been an absolute pleasure talking to you. Thank you for teaching us a lot about hyperspectral imagery and the use cases, and teaching me that there's now ultraspectral as well. And best of luck with Orbital Sidekick. And thank you again.
Yeah, it was a pleasure being on. Thanks for having me.
And that's a wrap for another nominal episode of the Space Business Podcast. Once more, if you enjoyed this, please leave us a 5-star rating on your favorite podcast platforms such as Apple or Spotify. You can follow us on Twitter at podcast_space. You can support us at www.patreon.com/Space Business Podcast. Lastly, if you have any feedback, including ideas for guests, and that may include yourself if you have an interesting space story to tell, or interested in being a sponsor, drop us an email at spacebusinesspodcast@gmail.com. See you for the next episode.